Fred is entering a contest to design an airplane. He came up with a design. This is the view of his airplane wing from the side. He thought with a curl at the back it would fly up more quickly. Unfortunately, on takeoff, his airplane did not lift. What mistake did Fred make when he designed his airplane? To understand this, we're going to learn about Bernoulli's principle. Bernoulli's principle says, as a fluid moves through a pipe of varying cross-section and elevation, the pressure changes along the pipe. So part of Bernoulli's principle, the part about varying cross-section changing the pressure, is related to the continuity equation. If you remember, as the cross-sectional area decreases, the velocity increases in a pipe. So this has a slower velocity than this, and as the fluid flows more slowly, it's going to have a higher pressure. Fluid that flows more quickly has a lower pressure. We'll give a few examples to show how this works. First, let's look at Fred's airplane. Now, the air on the airplane can be treated as a fluid, and as the airplane goes through the air has to pass on the bottom a larger distance in the same amount of time as the air on the top. Since this has a larger distance, it's going to be a larger velocity. Since there's a larger velocity, there's going to be a lower pressure. On the top, traveling a shorter distance, will have a smaller velocity and a higher pressure. The problem is that the air will want to create a force or a lift from the higher pressure to the lower pressure. In this case, there's going to be a push downward by the air. So to fix this problem, Fred should turn his airplane wing upside down. If he has the larger section on the top, it has a larger velocity on the top and a lower pressure. There's a smaller velocity on the bottom and a higher pressure on the bottom. This results in an overall lift towards the lower pressure. This is one of the things that will help an airplane lift. Francine is in her house when a hurricane passes over. When the hurricane comes by, there's very fast wind above her roof. The fast velocity wind is going to create an area of low pressure. If there is low pressure here and inside the house there is a higher pressure, what will happen? Before we find out, let's make sure that Francine can evacuate her house quickly. Francine goes to a safe area, and now the hurricane gets worse, and there will be an overall force upward on the roof of her house. This is how roofs will come off of houses during hurricanes. There is a common myth that if you crack a window and let a little bit of air come into your house, you can balance the pressure. The problem is that when you crack the window, you let that strong wind come into your house, and that's going to cause more damage than the pressure difference would. This is an example of what's called a Venturi tube. This tube is filled with fluid, and we have a larger cross-sectional area, so a smaller velocity, and then a smaller cross-sectional area with a larger velocity. The result is higher pressure in this section and lower pressure in this section. The way we can see that in a Venturi tube is if we open up tubes at the top, vertical tubes, and put fluid into them, you'll see that the level of the fluid held up in the larger cross-sectional area is going to be greater. D1, the distance that water fluid is held up is greater here than here. And that's because there's more pressure here to hold the fluid up. There's less pressure here, so the fluid will fall down. This picture shows fluid moving up a tube up to a higher elevation. This is the second part of the Bernoulli principle, which talks about as the elevation changes, the pressure changes in the pipe. So we have this point here that's a pressure P1 moving at velocity V1 at location Y1. This is just to show where the location is. We move up to a second location at Y2. The pressure is P2 and the velocity is V2. So we can relate these 2 points using the Bernoulli equation. The Bernoulli equation says the pressure at point 1 plus the density of the fluid times gravity times the height at point 1 plus 1/2 times the density of the fluid times the velocity of the fluid at point 1 squared. All of that together equals the pressure at point 2 plus the density of the fluid times the gravitational acceleration times the height at point 2 plus 1/2 times the density of the fluid times the velocity at point 2 squared. We can also look at this equation as a variation of the conservation of energy equation. This is the equivalent of pressure energy. This section is the equivalent of potential energy per unit volume, and it looks similar to our equation for potential energy. PE equals mgh or mgy. The only difference is we've divided by volume, so it's per unit volume. This is similar to our equation for kinetic energy, which is 1/2 mv squared. Here we have rho instead of m, so it's mass per unit volume times velocity squared. So this is saying that the energy per unit volume at this point is equal to the energy per unit volume at the second point. Since energy is conserved in these problems, we can also write the Bernoulli equation as P1 plus rho g y1 plus 1/2 rho v1 squared equals a constant. So no matter what point you go to, the sum of all the energy will be the same.